I have made this video on wave function, right? And we will try to understand how a simple harmonic wave can be expressed in terms of a mathematical function. So before we get into waves, let us try to understand what do we mean by the term function. Let us say we have a equation y is equal to x square plus 2. In this case, as we keep on changing the value of x, the value of y will change. In other words, y depends upon x. So the value of y would depend upon x. In such a case, we represent this by y is equal to fx, where f stands for function, right? So we say y is a function of x, meaning the value of y depends upon x. Okay. Let's try to find out the function, a mathematical function for a wave. So we'll begin with a pulse being generated in a rope. Let us say we have a rigid support, and this is a rigid support, and let us say this is a rope. This is a rope, and this is the free end of the rope. And let us say we apply a force in the upward direction on this rope. Right? When you do that, a pulse will be set up in the rope. So you will have a pulse like this, which will be set up in the rope, and this pulse will travel in this direction. Right? We will call this as the x-axis. So this is the x-axis, and this we will call as the y-axis. Right? This is y and this is x. So we have, if we look at the rope, we see motion in two directions. One is that motion in the x direction, and also there is a motion in the y direction. So if I look at any particular point, right, it has a displacement also in the y direction. It is not moving along the x direction. If I look at any particular particle of this particular rope, if I look at this particular particle, this particle itself does not travel along the x-axis, it just performs oscillatory motion around this particular point. And as this pulse travels, different points of the rope perform motion in the y direction. This motion of a particular particle in the y direction, it is dependent upon two things. It is dependent upon x, meaning where it is located, right? If I call this as the origin or O, then this distance is x, right? It would depend upon x, and it would depend upon time t. In other words, I am saying y is a function of x and t. Let us try to understand this, right? If I choose any particular particle, right, then its motion in the y direction, right, where it is in this way, whether it's over here, 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 or in this position, or in this position, or in this position, would depend upon where it is along the x-axis, right? And it would also depend upon time. How is it dependent upon x-axis? Let us try to understand this. If I look at this particular scene right now, this particle is not moving at all, right? There is no y displacement, whereas this particular particle has a displacement, right, this much y, whereas this has a displacement this much y, right? And the next moment, right, if this particular particle has y displacement this much, the next moment its displacement will change, because this pulse will travel further down, right? This pulse will travel further down, and this particle will come a little bit down. As it goes further down, the displacement of this particle will decrease. Thus we say that the displacement of the particle, right, in the y direction, or rather the value of y for any given particular point, depends upon x and t, where it is located along this, and at what time are we looking at this particular pulse. And this is represented as y is a function of xt. In fact, if you look at it closer, right, we can show that y is a function of x minus vt. Right? Let us try to understand by taking two pulses, or this pulse which has moved forward. So again, I am showing the rigid support, and I am showing this rope now. It is the same rope that I have talked about earlier. So this is the rope, and at any given point in time, let us say this is the origin O, and let us say this is the pulse, right? And this pulse after some time will be over here, right? Let us say this particular pulse is moving in this direction with velocity v. Let us say we focus our attention on this particular particle, right? This particular particle. So it is at a displacement y. And let us say this is time t equal to 0. So I am starting to analyze this particular pulse from this particular time t equal to 0, where this particle, let us call this particle A. Particle A is at displacement y, and the maximum displacement of this, right? This wave is moving forward with velocity v. So after time t, this wave would have covered a covered a distance of vt, right? Vt. Okay, let me first show this as x. This is x, right? This is its displacement from the origin, so this distance is x. After time t, it would cover a distance vt, right? And therefore I can say that this is vt. Right? So what would happen is that as time passes by, right, after time t, it is traveling with velocity v, and it would cover some distance vt. And let us say this particle again comes back to this same position as y, right? This would probably be the time period, because that would be the time for one complete cycle. So after vt, again we get back into this particular position. So what can I say about this thing? What I observe is that, let us call this as the old x, right? And I'll call this as the new x, right? Because now this is the new x, because the pulse has moved over here, so the displacement along the x-axis is again x. I'll call this new x. This was old x. So what I see over here is that displacement along the y-axis, which I call as small y, right, is same for old x and new x, right? So I have chosen this time t such that this particle comes into this particular position again. So same for old x and new x. In other words, I can write it is same for old x. Now what is old x? Old x is this, right, this distance. And can I call it new x minus vt? So it is x minus vt, the new x minus vt, and the old x is x. So y is same for x minus vt and x. And thus I can see that y is a function of x minus vt. Every time I move a distance vt, again I'll get the same displacement. Supposing I move further down a distance vt, right, again I'll have the same situation wherein the maximum displacement of y will be seen. And therefore I say that y is a function of x minus vt, right, which is generally written as yxt is equal to, or is a function of x minus vt. Right. So what we have shown that is, if a wave function is such that the y displacement is a function of x minus vt. Right. Now, if this pulse is periodic in nature, that means what happens is you will have all the pulses reaching their maximum position at fixed intervals of time. So let me again show the same diagram again. Let us say this is the rigid surface, and you have this pulse, and 2 and 3, and of course these are pulse which are going ahead, and this particular distance, right, is equal to v capital T. This is v capital T. This is again v capital T, where capital T stands for time period, right? So vt. So I get the same value of y for every vt, right? As the pulse moves ahead by distance vt, I get the same value of y, and therefore what we say is that y of x plus, say for example lambda t, is fx minus vt. That means if the x displacement is lambda, because the distance between two crests is lambda, this distance is lambda, right? Again this distance is lambda. So every time I move by distance lambda, I get the same value. Therefore yx plus lambda and t is a function of x minus vt, which we had already done earlier. And also yx t plus t is also a function of x minus vt. And this I can put together and write yx plus lambda t plus t is a function of x minus vt. Okay, to summarize, what we are saying is that for a wave function, right, for a wave function, the displacement in the y direction, this particular displacement depends upon x minus vt, right? And for every increase of lambda distance, or every increase of time period t, right, the displacement y remains the same, right? And therefore we come to this particular equation: y is a function of x minus vt, or any of these two. Okay, so we have looked at wave function for a simple pulse, and we have for a periodic pulse, right? And in the next video we will look at the wave function, how does it change when we have a wave moving in forward direction, a plane progressive wave moving in forward direction, and the particles are performing a simple harmonic motion. Thank you.